Welcome back. So, we are talking about satellite navigation and how to estimate the position, velocity and time, and we started with position estimation. In that we have seen that it is coming as a quadratic equation, so that ambiguities can be removed by a simple technique of linearization, where you have to have a approximate guess of your position and then iterate and try to find out your position. Now, like that you find out the position and with the iteration value, and it can be seen that it has been seen already that even if your initial guess is slightly away, within 2-3 iteration you reach to the to your required position with sufficient accuracy, with required accuracy. Now, time estimation. Time requires defined reference time and the elapsed time from the reference instant. Now, the time is maintained by navigation system is that is reference time. Satellite keeps the time. The time required for the signal transmitted at any reference instant to reach the user is also estimated, that propagation part. So, once these two are added, then you get the time instant when the signal reaches at the user as per the satellite clock. Okay. So, the reference time is coordinated time, that is UTC, or GPS time also maintained, that is maintained on the ground, and ground segment keeps track of the atomic clock standard, that atomic clock movement, that small del t. So, that error, and it calculates the difference and upload the satellite in the form of coefficients of a polynomial. So, that instead of correcting the clock on the satellite using additional circuitry, it simply sends a polynomial or the correction parameter, so which will be broadcasted to the user. User obtains the difference between its own clock and the satellite transmitted time and can correct the clock to the satellite time, and also it obtains the bias between satellite and the reference time, which was modeled and uploaded, and adds the same to get the reference time. That is how user gets the time. Velocity estimation is much simpler, that is the pseudo range rate can be found out from the Doppler, and the Doppler shift is pseudo range divided by the wavelength, and the pseudo range rate of the ith satellite can be found out in that form, and that derivative form of our earlier quadratic equation. So, in terms of range rates of satellite and user positions and time, it can be found out. This can be solved using a set of 4 equations, similar way as the position determination that we did. So, therefore, the satellite navigation receiver needs to solve 8 unknowns, x, y, z, del t for the position and derivatives of these 4 for velocity. So, pairs of measurements, the parameters and its derivatives from at least 4 satellites are needed. So, these measurements are called observables. So, basic assumptions of this PVT estimation, let us recollect, that is satellite position must be known with sufficient accuracy. If that is in error, your position is in error, because you start with the reference is the satellite. At the time at which the signal are transmitted from the satellite must be known with sufficient accuracy. If that is in error, you are also in error, because you are finding the range with respect to the time and the propagation time, and there are other significant sources of error which needs to be considered. We will see what are those different errors. Now, let us go to the signal what is transmitted from the satellite, that is GNSS, that is Global Navigation Satellite System signal, that consists of carrier power, the navigational data, the ranging code, the carrier frequency and phase, and it can be mathematically expressed as, let us say, YIT, ith satellite signal is root 2 CI, that is the amplitude, the DIT, I stands for the ith satellite, DT, CT, and cos 2 pi ft plus phi, where that root 2 CI is the carrier power component, the navigation data component is DIT, navigation data which is being broadcast, which contains the satellite ephemeris and other models and other polynomials, etc. The code is the ranging code CIT, and that ranging code consists of a PRN code unique for a satellite. So, satellites are identified by the PRN code instead of satellite number, that provides the timing and the spectrum spreading. So, all satellites use the CDMA mode of communication, mostly that is GLONASS had FDMA, but they are changing over to CDMA. So, most of the almost all the satellite navigation system are using CDMA mode of communication. So, this is that ranging code which uses both the purpose of overlapping over the same bandwidth as well as unique identification of the particular satellite as well as time mark. And then the carrier frequency is Fi and the phase is phi I. Now, ranging code should have good autocorrelation property, obviously we know, and autocorrelation property R tau is expressed Si and Si minus tau is expressed like this, and ideally the autocorrelation peak is known to you. Peak should be peak value should be at 0 delay and 0 value at elsewhere, and it should have a low cross correlation property, because all other satellites are transmitting at different peer encodes. So, to allow all satellites to transmit at the same frequency band, the ranging codes should have low cross correlation property, that is SMI or SNI minus tau. If you sum them, it should be 0 ideally. So, SM is the mth satellite, SN is the nth satellite, where m is not equal to, it is not the same satellite. This is a format in which the navigation message is transmitted. It comes very slowly. You just see the 300 bits of information at 50 bits per second. It takes 6 seconds to come the complete message of 300 bits, and it is divided into many subframes. So, each of the subframes, TLM is telemetry, HOW is handover word, then GPS week number. When first GPS was launched and service started, from that weeks are counted. So, how many weeks have elapsed, then satellite vehicle accuracy, its health, the clock correction terms. Then the subframe 2 and 3 contains the ephemeris parameters of the satellites, and then subframe 4 contains the health data of satellite extra satellites vehicles, which are this is GPS actually. So, they have 24 satellites, it's 25 to 32 satellites. What are their health position, special any other message, ionospheric and UTC data, certain models also sent. So, like that many other additional information are broadcast, but most important thing are these two, subframe 2 and subframe 3, where the ephemeris are transmitted. So, as we have seen that it is to be extracted separately and used. Now, at the receiver, the analog signal is delayed and Doppler is added, satellite is moving, the user also might be moving. So, Doppler is added to it. So, it is the same equation from all the satellites I equal to 1 to L, the root over 2 C I, it is d I t minus tau, C I t minus tau. So, this tau is the delay, whereas reference FRF, the frequency on which it is transmitted, it is Doppler delayed by f d, that ith one. So, and then phi I. So, that is the tau is code delay and this is the Doppler delay. So, the receiver has to search not only for the code to identify which satellite it is, it has to also search for the Doppler. So, it has a search space. So, in that search space it has frequency beams as well as it has time beams. So, digitized information which is available where the energy is maximum, let us say here this is the y, it goes on searching in frequency domain and time domain and finds out this beam. So, it is a acquisition process is involved, and once it is acquired, it takes some time to acquire, time to first acquire, and after that it has to track that. So, because of Doppler it might be moving, the position might be moving, code delays are also changing. So, therefore, it is acquisition and tracking, both the functions are required at the receiver. So, it needs a signal processing. So, signal quality, the demodulator should have adequate SNR and SIR. We will do a quick calculation, try to see what is the quality of the signal for required. This calculation is obviously known to you, the methods are known. Let us say CNR is estimated at the receiver input, and noise power primarily depends on the input noise through the antenna as well as that is the noise figure of the receiver and the bandwidth, which is our KTB, that is noise power. And let us say T is 273 degree K, 2 megahertz is the bandwidth. So, K is known. So, noise power is minus 141.2 dBW or 7.59 10 to the minus 15 watt, and the each signal is of the order of 10 to the minus 16 watt, which is received at the receiver from the satellite. So, the 9 of the satellites, assuming all of them are interfering with the same power. So, 9 times of this, which is minus 150.5 dBW. So, noise plus interference, CDMA is acting as the interference. So, noise plus interference in the in numerical terms, these values can be added and you can get 8.5 in 10 to the minus 15 watt, which is minus 140.7 dBW, and your signal is minus 160 dBW, that is 10 to the minus 16. So, C by Ni is minus 160 minus 140.7, which is minus 19.3 dB, which is very low. The C by Ni is lower. The CDMA helps you. So, which is of course, now the bandwidth is 2 megahertz, which is 63 dB hertz here, and subtracted. So, C by N plus I naught is minus 73.3 dB hertz. So, CDMA gain, processing gain, has to be 30 dB. With the processing gain of 30 dB, you get a minus 19.3 plus 30 is 10.7 dB SNR at the correlator output. Your receiver will work up to that. So, that is the CDMA advantage, what you are extracting out of it. With a 2 megabit spreading, you get 30 dB, right? Just a quick calculation. Let us go back to our the receiver block diagram. Is it has an antenna, mostly need not be fully omnidirectional, but at least you should look at the sky. So, it is antenna, and the RF front end, which has the RF amplifiers, etc. And then after digitization, it does the acquisition tracking, we told you, in the search space, and then once it is data is found out, it goes into navigation processing. It extracts the data, tries to do that linearization, find out its position, velocity, and time. Now, sources of error. Let us see what are the types of error that can come. Control error, which is the ephemeris error, space error, which is the satellite clock stability and clock code bias, and the propagation error is ionospheric propagation delay, tropospheric delay, multipath. These are all variables, and that the user receiver noise and receiver bias also can act. Now, control and space segment error is ephemeris and clock parameters computed at the control segment and updated at certain intervals when it is visible to the control station, satellite is visible. So, in between it will slightly drift. So, that is the control error. Errors in the estimation of the parameter, when you estimate that also there is a model, because of that some error may come. These intermediate positions are predicted using last updated data. Errors grow with age for the prediction, and the radial error is smallest, along and crosstalk errors are several times larger, etc. Now, in the propagation path, there is important thing, which is ionospheric delay. That is, ionosphere has different refractive index than free space, and electromagnetic wave travels with lesser velocity than free space. Hence, using free space velocity of for ranging causes error, and at this particular frequency normally, which is allotted for this satellite navigation, which is L band, the ionospheric error is quite dominant. At much higher frequency, it will be much less. And tropospheric delay is dry and wet components, the gases and vapors, they also try to delay the signal. So, therefore, there will be certain error. Scintillation is a phenomena which is a large fluctuation of signal strength in short term, that is formed by the small scale disturbance in ionospheric, that is electrons, or in tropospheric region by the gases, etc. So, that also affects something. Multipath is fluctuation of the signal strength due to the reflections, incoherent combination of the signals coming from different directions, reflections and scattering. User receiver, as the signal passes through the hardware from the antenna to the actual processing, the receiver, it experiences some delay, and they add up in additional propagation delay, and hence introduce the error in ranging. In addition, there is also the receiver thermal noise, that also has to be considered. So, the true range, if we call it capital R now, due to different errors, the true range from satellite receiver is not known exactly. So, it is a pseudo range, we have already used this term. So, pseudo range is the R plus the clock drift delay, clock error, iono error, tropo error, and all other errors together. So, now we have understood that there are certain errors, and this has to be estimated, modeled, or corrected. How do you do that? That is, error correction is the wrong solution of the position unless the error terms are removed. The correction error term can be done, correction can be done in two ways, either by direct estimation, estimate and model it, and made use of models, or real time measurement. correction can be done with respect to a reference receiver, okay, which is called DGPS, differential GPS. Now, direct estimation is clock bias can be removed by the modeling of the clock movement, and that can come through the navigation message. Already we have said that. Ionospheric error can be single frequency. Users can correct ionospheric errors using a model of the ionosphere at that location, because ionosphere varies at different places in the world. Dual frequency, there are 2 frequency receivers can be there. So, dual frequency users can calculate the ionospheric error and correct it, because both the frequencies will have some similar type of error that is coming in. Tropospheric error can be used with a wet and dry tropospheric model, and receiver bias error can be, it changes very slowly, but it has to be corrected. It can be corrected by estimated a priori offline measurement of the receiver bias, and then at certain interval you can correct it. Estimation may be updated at large interval. The effect of error in measurement is ranges are ambiguous with certain width. Effect on position determination depends on time, depends upon the relative orientation of this error, geometry of the participating satellites. These effects are measured in terms of dilution of precision. It provides the relation between the range error and the position coordinate error. You can see that if the satellites selected for the PFT is located very nearby, then you can imagine that cross section points for all the spheres will be slightly fuzzy. If they are away, it will be much sharper. That is what is DOP. DOP depends upon the geometry of the participating satellites. Wider separated satellite lead to low GDOP, geometric DOP. GDOP is related to the volume contained by the tetrahedron formed by the joining the participating satellite and the user. This is a simpler way of explaining the thing. It can be mathematically also done. We will not go into the details of that. Now, differential GPS techniques are used to reduce the position error using additional correction data from a reference GPS receiver situated at known position. Previously known estimated well surveyed point is known. Range error can be estimated at the reference receiver. Estimated error will be transmitted to the nearby user, and these errors are used for correction of the range at the user. The error components may be common to the reference as well as the user. It can be correlated or it is independent. Let us see. I mean, DGPS does not correct all the errors. That is what is the meaning. There are 3 types of error components, and cancellation of the range errors leads to the accuracy. Okay. So, how it is done? There is a reference at this point, which is ground reference, well surveyed point, and there is a GPS receiver which is receiving from 4 satellites. Now, if user selects the same 4 satellites and he is getting the signal, and user gets some error, since this reference station knows its own position, is well surveyed previously a priori known, so he knows what is the error he is getting from these 4 satellites in this 4 propagation path. So, that error term he transmits to the user by another link. So, this correction term comes and the user corrects it. But as we said, there are certain common errors between these 2 reference station as well as the user, mobile user. There are some correlated terms and there are uncorrelated terms. The common errors are satellite ephemeris error, which is completely removed because the same 4 satellites are selected. Correlated errors are the propagation errors. If they are close by, then the signals from these satellites to the reference as well as to the mobile user are paths are more or less passing through the same part of the ionosphere troposphere. So, they can be assumed correlated if they are close by. If they are farther away, it cannot be removed. So, it can be, therefore, it can be said partially removed. Cancellation degrades with the distance. And uncorrelated error, multipaths. Multipaths will be different to the reference as well as the mobile user. It cannot be removed at all. So, differential GPS is not the full solution always, but it definitely improves. Now, let us talk about global navigation satellite system, which is a worldwide PVT determination system. By combining all existing resources of the satellite navigation, people try to use GPS GLONASS combined receiver, Galileo GPS GLONASS combined receiver, like that. So, you have more number of satellites. So, you can select the best satellite looking at the GDOP of different types of constellation satellites. So, one or more satellite constellations are used. Distributed control segment unified user receiver, and there are augmented system enabled to improve the performance. Now, I will briefly talk about what are some of the parameters and features of the GPS and other constellations. The GPS constellation has 24 satellites in circular orbit, 6 orbital planes at different inclination of 55 degree each, and the period of the orbit is 11 hour 58 minutes. Semi-major axis is 26,500 kilometers. It's not geostationary orbit, it's a medium earth orbit. 4 satellites in one plane, unevenly placed, not evenly placed. These they did it for that GDOP improvement over the service area what they have looked into. And eccentricity is mostly circular, so eccentricity is very low, it's 0.02, and constellation allows at least 4 satellites visible to a user most of the part of the earth. Typically 6 to 8 satellites are visible. Another constellation is GLONASS, Global Navigation Satellite System, which is by USSR, now it's Russian Republic. It has also 24 satellites. It has 3 orbital planes. Phase plane separations are 120 degree and 8 satellites per plane. It's also medium earth orbit, 25,000 kilometer. Orbital period is 11 hour 15 minutes. Inclination is 64 degree. This inclination is selected based on their service area, which is much higher latitude. And they are transmitting 2 frequencies. Of course, now they have changed. Now this is a FDMA technique they used, and ranging codes are this CA code is course acquisition code, and P codes is precision code. These are also used by GPS. I have not mentioned in earlier, so their frequencies are mentioned, and modulation is FDMA. But now they are changing over to CDMA. The Galileo, which is European Space Agency, is 27 plus 3 satellites. These 3 is extra satellites on orbit spare, and 3 orbital plane, 120 degree separation of the plane, and 10 satellites per plane. This is slightly higher orbit, 30,000 kilometers, based on again their requirement. And 14 hours 22 minutes is orbital period. Inclination is 56 degree, and frequencies of 2 different transmissions are given, and modulation is CDMA. Now, in addition to that, there are Compass as well as other satellites. India has started launching its own satellite, which is regional satellite. So, it is called Indian Regional Navigation Satellite System, IRNSS. You must have seen the announcements and advertisements whenever they come up. Any satellite is launched. Recently, they have completed the constellation. That is, configuration is 3 GEO satellite. You try to recollect, it is geostationary satellite. So, their locations are known, which is approximately 35 degree east, 84 degree east, and 130 degree east. So, it is a regional system. So, therefore, it is not covering whole earth, only covering only Indian region, India landmass as well as surrounding ocean, nearby ocean area. There are 4 GSO satellites. These are geosynchronous satellite. So, they have certain inclination. You can imagine that tetrahedron, all of the satellites, if they are on the same plane, you will not get the proper GDOP. So, therefore, there have to be some satellites which are away from the equatorial plane. So, that is why this inclination is given. So, 4 satellites are there with 30 degree inclination at 55 degree east and 111 degree east across the equator. That is total 7 satellites, and their master control center has to be more than 1, because if one fails, the other one takes care. And that range integrated monitoring system, which is required for the control segment. IRNSS reams are almost about 20 numbers. I am not sure exact number about it, and there are command station more than 5 numbers. These data were collected some times back, so it may have varied now. So, we have mostly taken the reference of this linearization technique. It is available in many books. Here we have referred to a book which is Understanding GPS by Kaplan. So, with this we have covered what is meant by PVT, and what is the trilateration technique using the satellite, and the time and velocity, how it is estimated in addition to position, and then the basic functions of GNSS very briefly. You can see it in Pratt also, the book textbook satellite communication. There also is chapter. there also you will get some of the information, and errors and their mitigation we have talked, DGPS and other modeling technique, and some existing sat-nav system. So with this we complete this satellite navigation, which is as an application of the satellite communication. So till now we have covered almost all the topics what we announced. That is, our initial part is the introduction, then orbit, then the space segment, the link budget, then the propagation, and then multiple access, and then the linear that is non-linearity and certain issues like non-linearity and synchronization issue, and then of course the higher layer effect on the higher layer. These are a couple of issues I briefly touched, and of course one of the application. But it's a vast subject. In this such a short time, everything cannot be covered. I hope you enjoyed the course. Thank you very much.